call myself a chief technology architect because I work for the office of the CTO. My boss is Brocade's CTO, although we've got a few of them. And then we have regional CTOs. So to distinguish myself from the CTO for EMEA, I'm the CTA for EMEA. And Brocade has been was a founding member of the ONF, and I was their representative from the early days. And then after about a year, we established, maybe it was a year and a half, we established the Forwarding Abstractions Working Group, which was aimed at solving interoperability problems that we were anticipating. Because if you know the history of OpenFlow, OpenFlow 1.0 came out in, I think it was New Year's Eve, 2009, the last day.
Okay, the corrected file, TTPs.zip is on here, so some other marketing stuff, but you don't have to copy that, except it's really important. No.
So yeah, well that's going around, and then as you'll see in the slides, I'll do some background, and then we'll go into an exercise. But first, yeah, we're doing this introductions to tell you who we are. So yeah, I was the original chair of the Forwarding Abstractions Working Group, and my vice chair at that time was David Meyer. Then he was at Cisco at the time. He came over to Brocade, and so then I got a different vice chair. But then there's been a few changes at the ONF, and now the Extensibility Working Group and the Forwarding Abstractions Working Group. Extensibility was responsible for the OpenFlow switch protocol, and of course Forwarding Abstractions did TTPs, and they merged, which I think is a wonderful thing, because we weren't always working in the same direction, the protocol group and the TTP group, but now we're one group, open data path, and I think we're a little bit more aligned. You know, it's going to take a while for all the differences to be ironed out, but I'm very excited about that transition. So that's me. Oh, and just a little bit more difference. I got involved in networking in 1995 as an ASIC design engineer and then ASIC architect. So I definitely started at the bottom, you know, where you look at the bits of the packets. I'm not the guy who knows 482 protocols at layer 4 and above. I know a few protocols in the layer 3, 4 range, but not like the real top-down guys. So I'm more of a bottom-up guy. Who's next? Just give us a... Huh?
Start from this?
Yeah.
Right. All right. So yeah, I'm Victor Larin, and it's my colleague Evgeny. We're both from the FOSS networks here. And so again, the companies, we also have the deep background telecom experience in previous life, but now enjoying the all of it, say, open source solution, but using in telecom environment.
Excellent. I guess you're covered?
Yeah, both Russian ones.
Ah, yeah. Okay, next.
I came here late. We are introducing ourselves. Right?
Yeah, that's all.
Okay, I'm Luis Blanco. I work in the telecom. Just to see how things go.
Okay.
My name is Mo. Everybody call me Mo. I'm another one trying to catch up. My background is network design and architecture for the old guys. So,
For what?
for the old guys.
Ah,
So I'm trying to catch up in the world.
yeah, it's moving for a change, right? I mean, it seemed like there was always some new protocol, but now things are a bit more dynamic and unpredictable. Can you introduce yourself just briefly?
So, yeah, my name is Ivan. I'm from Moscow. I'm privileged staff. I'm an architect. So, and interested in the TTPs especially because I'm architect for our SDN applications as a part of this project, actually.
Ah.
So I know how it's really hard to do the pipelines and so on and so forth. It's nightmares, I know. So it's the reason why I'm here.
Good, excellent. Next, where do we start? Yeah, we'll start here then.
My name is Mauro Di Francesco. I work for Ericsson in Ireland. I'm part of the solution architecture team that does mainly cloud and IT. I come mainly from a cloud IT perspective, doing data center automation and, let's say, trying to port what is called the Amazon model into the different data centers. So one of the main barriers now is the network, obviously, and that's where we're trying to find out the different
Yeah, Amazon said that, right? The network's in my way.
Yeah.
Yeah.
Good morning, I'm Benjamin from PCCW Global. I come from IP network environment and design, and yeah, try to keep up as well with the new technologies and see exactly what we can do and what exists.
Excellent, thanks.
My name is Florian. I'm working in Dell as a senior support engineer, and I'm trying to get myself more familiar with SDN and NFV, and it's a very exciting topic. And yeah.
Okay, good.
I'm Registration from Water Technology, and I'm SDN System Architect.
Good, welcome.
My name is Minasa from Korea. I'm working for the TTA. TTA means the Technology Telecommunication Association. The TTA in charge of making a standard in Korea. So I'm charging the testing and certification in IPv6 in Korea. So I have a new mission to understand the OpenFlow, so I can use.
Oh, good. Thank you all for coming, and I think maybe there's someone else coming, or at least, unless that's somebody else's laptop. Maybe if nobody comes, we'll just auction that.
Raffle.
Yeah. And I know Marcos, and I know, what's this guy, the guy in the white shirt? Yeah, that guy. So the presentation today, it tries to be a little bit general. It even has stuff in here that probably makes more sense for a developer. You know, and there's actually many developers, of course. There's developers on the switch side, and there's developers in the controller space, and then there's application developers as well. And so trying to cover a lot of ground. But I think we'll see about TTPs and how they play into interoperability. And I think everybody here will care about TTPs, but maybe not everyone here will be creating their own TTPs. They may want to like understand the difference between two TTPs, you know, I expect probably someone in this room will create a TTP, but probably not everyone will create a TTP. So the way I kind of think of it, you're familiar with Netcom and Yang models? And so I'm curious what you say, because to me TTPs are like Yang models. You know, they're very important to Netconf. TTPs are very important to OpenFlow. But how many of you have actually created a Yang model? Okay, so it's like that, yeah, but other people have not created a Yang model. Even though you know what they are and you use them, right, you care, you know, do the two devices, these two different devices, do they use the same Yang model or not, right? And usually they don't, but I think maybe a little bit more often they will, we hope, right? So it's kind of a similar concept with TTP. So, I think the USB stick went around. Did you try the new TTP? I'm curious, I just want to make sure that the TTP.zip is not corrupted. So give that a try. And so I'll be talking about, I think I lost my, my slide that told you, oh no, here it is. Basically, this is a slide. So I'll do an overview, basically background, talk a little bit more about it. That's probably the main part I want you to take away is like how TTPs help interoperability. Then we do an exercise where we manipulate a TTP, and I do think that's helpful because it gives you more of a sense for what a TTP is. Even if you're probably not going to be modifying TTPs a lot, I think the tools will be getting easier over time, and so the idea that you could modify a TTP, that's not that crazy. But because of, you know, of course you want your TTP to work with a bunch of other software and so on, I think unless you're in something like a development role, it's a little less likely that you would change the TTP. But I may be wrong. So I think it's good to go through this exercise, and then we'll go back and take another look at TTPs again. This isn't true, so this is left over. I haven't uploaded that to the, I think this link is not correct. These slides, by the way, are also on in the smaller zip file. The two zip files you have, I forget the name of one of them, L123 something, is a bunch of smaller files, including the TTPs and the PowerPoint, so it didn't take up a lot of space. The big zip, oh, Rick?
I was just going to say, when we're done, we'll have this video and the slides inset. They'll be up on ONF's YouTube channel. So
Okay.
probably give us, till middle of next week.
The larger zip file is actually one of the builds of Open Daylight, and or a smaller piece of it. So there's a TTP project in Open Daylight that's working to integrate TTP capabilities into Open Daylight, and we do a special build so that there's a separate artifact that we call the parser. So you can basically import TTPs and manipulate them a little bit without using the full controller, which is kind of slow to launch and so on. So anyway, that's why you have two zip files. It's not required that you even install the TTP zip file, but we can do a little bit of exploring with that. So first, the overview. So SDN, right from the beginning, said we're going to decouple hardware and software, actually control and data plane, which I think of as hardware and software. We're going to decouple the control and data plane, but that wasn't just a question of physically separating them, right? To some degree, that notion of physical separation had been around for a little while in a number of other protocols. Some of the CAP-WAP and other kinds of things had a little bit of separation of control and data. But I think the real driving force behind SDN was that you could buy these from different vendors. It was really coming more from the customer side, the big operators saying, we're tired of being stuck between this vertical choice and that vertical choice, and you can't, every time if you want to have a multi-vendor environment, there's a lot of pain involved, and I would like to be able to choose my vendors based on, that they're the best solution for any particular situation and not have to always fight about, interoperability. Yeah, sure, they interoperate at the data layer, but when you start getting up the control and management and other configuration, then the interoperability starts to get more and more painful. So to me, this was not just a technical question, this was really more of a market question, right? That we want this kind of interoperability. And a standard low-level control protocol like OpenFlow, that was the place to begin. And OpenFlow 1.0 came out. You could do a lot of demos. There was a few vendors even before the standard really got going. There were a few vendors. I know HP Brocade was not one of them, even though we were a founding member of the ONF. OpenFlow 1.0 was out a year and a half before the ONF, right? So, and in fact, 1.1 came out the week before the ONF started, and that was kind of interesting, as we can kind of talk about. But I want to talk a little bit about pipelines. Packet processors like ASICs and other things that forward packets in our switches and routers, they have a processing pipeline, a packet processing pipeline, that it goes through stages. And often those stages are very short stages in terms of like a chip. They happen in like nanoseconds. It's just a few clocks and they move through their processing pipeline. But there's often like 5 stages or 6 stages or maybe 7 or 12. But the OpenFlow 1.0 packet processing had a very simple pipeline, right? If you're familiar with OpenFlow to some degree, you just took a training from Marco, and they had a single stage essentially where the flow table has match terms and it checks the packet against those matches. And if it matches, it'll find the best match, the highest priority match, and then it'll do the actions that are listed in that flow entry. So it'll only match one entry in this table. The table might have thousands of entries, but it'll match one complicated match and do a set of actions, and that's it. So that's basically a single table, a single stage pipeline, and so that's what I draw with a simple picture, a very simple pipeline. That was OpenFlow 1.0, and it's in many ways quite powerful. If you see that a number of use cases were supported with 1.0, but at the same time, there's a lot of things you can't do with 1.0. Some of it is because like it had no IPv6 and so on, but other thing is because it didn't have enough tables. This was, of course, recognized before the ONF, because OpenFlow 1.1, which was before the ONF was launched, because the ONF sort of existed quietly a little before that, but it was launched in March of 2011. Anyway, 1.1 offers 250 tables, right? You can, that's more tables than real chips have. So real chips have more tables than OpenFlow 1.0, but less tables than OpenFlow 1.1. This 1.1 allowed for much more complexity and much more power, but it didn't really recognize how you deal with different ASIC pipelines. So, you know, the diversity of real pipelines that are in real networks and real data centers everywhere. Almost everything in, you know, almost all of our network equipment is ASIC based. The alternative is like network processing units. They're really more soft oriented. Basically, they run code, and you'll sometimes hear this phrase, they run to completion. And that means you don't know exactly how many clocks, you can't say precisely how long it'll take to process it, and so latency and so on is different. And so there's kind of a trade-off, historically, a trade-off between the ASIC and the NPU kind of chips. And so OpenFlow 1.1, that works okay on the NPUs, but most of our equipment does not have NPUs. So this was kind of a challenge, and this is what the people at, you know, folks like me and other colleagues that helped create the forwarding abstractions group saw that this was a little bit of a problem. So taking a step back, OpenFlow is about control. It's not about defining, it's not about creating a pipeline or describing a pipeline. It's about how do you control the pipeline. And of course, to control the pipeline, you kind of got to know what the pipeline looks like. If you have an NPU, a network processing unit, you can make a pipeline be kind of whatever you want. But if you have an ASIC, you don't really have that kind of flexibility. We need to kind of have a good understanding what pipeline we're talking about. And in some cases, you don't have to, well, I'll show this in the next couple of pages. So basically, as I said, in OpenFlow, in this community, we don't often talk about pipelines, and this is what I'm trying to change a little bit so that we're at least aware of pipelines. We don't have to look at them really closely, but we have to agree on the pipelines. So TTPs are basically a way to kind of describe a pipeline model, and we do it in OpenFlow terms. So we talk about the same tables, and we talk about the same match fields and the same action fields. And we say, you know, these are the tables that are part of our pipeline, and these are the matches and the actions that are valid or expected in, you know, table 1 or table 6 or table 9. If we don't have TTPs that explain what the pipeline is, there's so much, too many possibilities, too many variables, and it's too difficult. It's difficult on the switch side because we don't know what messages we have to support. It's difficult on the application side because we don't really know what the switch looks like without a TTP. So here's an example of a couple of pipelines. This is just, it's becoming to be a common way to talk about pipelines, especially in OpenFlow. In OpenFlow, each stage of the pipeline uses one table. In real chips, there might be more than one table active at the same time, but we don't go into that level of complexity with OpenFlow. We just assume one table at a time. And sometimes it may look like there's many tables, but it'll only handle one of these tables. It doesn't try to do like 3 at once in OpenFlow. In any case, these are a couple of different pipelines. Now, as it happens, both of these, they come from a Broadcom document, and in fact, that PDF is in your in the thumb drive, so it's in the smaller zip file. And what's interesting about this is Broadcom has created a very powerful pipeline, abstract. In other words, this is not, well, I should be careful. They have very powerful silicon, but what I'm talking about here is an abstract pipeline that is compatible with much of their silicon. I don't know how much of their silicon, but I think more than one family, definitely more than one chip. This complex pipeline is actually capable, it can do this, and it can also do that. I don't know if it can do both of them at the same time, maybe. But for our purposes, it's often better to just think about a simple pipeline. So we'll just like here's 3 flow tables, and then these are group entries. So the pink ones or orange or whatever color they are, those are flow pipelines, and these this other color is the group entry. So this I think is just a simple bridging use case. It's got some multicast and looks like tunneling. And this one over here, does it have MPLS? No, it includes routing. I know they have other ones that support MPLS. So they have a series of different pipelines that they use for different use cases. And really the same chip supports all those pipelines. So this sort of simple pipeline, because the whole thing is maybe 20 tables or 25 tables. But if we look at a simple use case, overlay tunnel use case, 3 tables does the job. And there's what, 7 tables does the job. 7 is a little bit complex, but much less than 25, right? And the point about this is it helps for the app developer to understand what picture they're using, and it helps for the switch developer to understand the picture as well. But we didn't have that in classic OpenFlow. So I call this a framework gap. You know, we had just a space between our, we need to fill that in. And that's what the Open Data Path Working Group or the Forwarding Abstraction Working Group was, to figure out a way for the controller and the switch to have an agreement on what the pipeline is. And that's where we conceived of these table type patterns. And as I said, they're models that talk about the pipeline as a set of supported control messages, a set of tables that support certain control messages. And it turns out there's kind of two ways to focus a TTP. Maybe there's a spectrum, but really, in practical terms, you either try and define a TTP as what the application needs, like if we look back here, you know, this is a TTP it kind of resembles a certain use case or a set of use cases that are very similar. And you could make that one TTP, or you can make that one TTP that's focused on a different use case. In fact, then there's also the ability to make a TTP that's focused on the device. And often that's going to be a much more complicated TTP. So the Broadcom's OFDPA, they have a TTP that goes 20,000 lines. It's huge. It includes those pipelines, but it's really focused on Broadcom chips. That TTP, the OFDPA, doesn't really work on like Marvell. It doesn't really work on Intel. It doesn't work on Brocade's chips because it's really focused on Broadcom. But if we look back at these pipelines, this is pretty generic pipeline. If you only had a 3-table pipeline, this probably also works on Marvell. It probably also works on Brocade and so on. So this is kind of an application or a use case pipeline, and yet the whole OFDPA is really a device pipeline. So that's what I'm saying here is that there's both kinds. Conceptually, we can have a sort of a simple model of a pipeline that we can use to code from, write SDN applications. Or we can have that complex thing that says, here's all the features of my chip, and here's how you can control it with OpenFlow. And that's much more complicated, especially for modern chips. Years ago, I think they would have been simpler, but now they're super powerful. So we created this TTP spec that describes, allows us to describe pipeline models. And they're basically text files. We'll see a picture of them. We'll manipulate them a little bit, not directly in text though. And we represent these in JSON. Are you familiar with JSON? JSON is, okay. If you don't know, it's JavaScript object notation. And it's a pretty simple text file. But we also we intend for the spec to also be supported in XML and other formats as well, because basically it's just sort of a name-value pairing with a bit of structure to it, you know, and some keywords. And so it's not hard to represent it in both forms. And we have done some XML stuff. We're looking at also supporting YAML and so on. And there are, I don't know, it seems like different situations where someone might prefer JSON or XML. And that's why we didn't want to just force one or the other. So we'll take a look what they look like and how they help more with interoperability. Oh, well, no, I guess we look at the file in a minute, sorry. So the original picture was, and so if you look at the early spec for TTPs, the one that came out 15 months ago, 16 months ago, the idea was that the controller would understand different use cases, and the devices would offer, they would support some of those use cases. Essentially, you'd have a driver that said, okay, well, there's use case A, and I'll have an agent that supports use case A and another agent that supports use case B built into the device, so kind of like a driver-side model. And we came at it that way because we kind of had a switch mentality in the ONF. Most everybody that was a member, there wasn't like controller members, really, there weren't a lot of controller members or application members. It was mostly switch vendors and then operators. But we didn't have a lot of representation here. So we focused here, but this turns out to have, it's not the best idea, which we didn't really think about at the time. The problem is we need to be able to do, should be very soft. We want to be able to change the agent, change the model in the early days while we're experimenting until we figure out the right model. And the problem is that devices, well, they're not really great environments for third-party code, right? They don't upgrade the software like the vendors. They upgrade the software every 6 months or maybe every 9 months. And they don't want to have to try and figure out, okay, which TTP can I support and which TTP should I support? There might be 2 or 3 different tunneling TTPs. Oh my God. So that model, even though conceptually it works, from a practical perspective, having a lot of agents here turned out to be kind of a challenge. So like, I just repeat this, right? It was burdensome on switches. We thought they would natively support a lot of different TTPs, but that's more challenging. Instead, it's more like the Broadcom model. Let's say the switch only supports one TTP, and it is kind of the native TTP. It's the vendor TTP. Then it's not so hard. They get it right one time. They're in control. They don't have to follow the market, etc. And then instead we do some mapping, which I'll show in another picture here. So this is really a messy picture, but it's actually a simpler job. So now we can say, well, imagine this is the Broadcom TTP, and it's supported by a bunch of Broadcom devices pretty clearly. And same, okay, we got a Marvell and an Intel, and then we have those other cases up there. But we can do the translation between the use case and the device in the controller. That's a much better development environment. He's shaking his head, oh man, this is never going to work. But in fact, we're making good progress with this, particularly in Open Daylight. ONOS has done a similar model. They have another, did you hear about flow objectives? ONOS talks about flow objectives. They're pretty similar to these TTPs, a little bit different. There's no spec, so it's hard to say exactly, but it's conceptually a similar idea. I think maybe it's a little bit more abstract, so it's possible that they fit into this picture in addition to TTPs. But where this is going is that they'll have that like simple 3-table model, and then here's the 25-table model. Which 3 tables, these 3 tables map to some tables in this picture. How do you figure that out? And we're trying to figure out if this is both written, if this is a TTP in JSON and this is a TTP in JSON, we're working on code that will help figure out that mapping. Not completely automatically, so probably an engineer or somebody would have to look at that and say, yeah, that's the right way to do it. So this should be something that we can do like in an afternoon. And then there should be, we expect to be able to do some testing in, or maybe analysis is a better word, so that you can confirm, you know what, yep, if we do this right, these two things do the same thing. And that way you can now control this use case, you can control a bunch of different devices using one use case. And finally, we get to the place where we can control, you know, device R and device S and device T without writing a lot of code. Because we don't have to rewrite TTPs. They're fairly stable. We just run this mapping tool. And once you run the mapping tool, and who should run the mapping tool? I think the vendor should run the mapping tool. But they, you know, when there's a new TTP, if they want to support that TTP, they can do some mapping and testing before. I mean, it doesn't take a lot of code, so that their device doesn't have to change. If they see a new TTP, they can evaluate whether we can support that TTP, and it could be, you know, several weeks after this OS is released, and you don't have to wait another 6 months for the next OS, and you don't have to change the device, because what happens every time you change the code in this device? There's, you know, 6 weeks of QA and testing and analysis. So moving that out of here makes it much easier. And now we can just change the mapping code up here. So this is the new model, and it was really, it really was based on, you know, I'm glad we got out the spec. So we got out the 1.1 spec 15, 16 months ago. Welcome, guys. I'm glad you could make it. These slides are, oh, we should get you the thumb drives. We have, here comes Rick, he's going to hand it around. There are a couple of zip files on there, and the smaller zip file has these slides in it. So, and you know, actually I should have said that at the beginning, that we have, I think we have plenty of time. I've done basically the same workshop in about an hour and 15 minutes or an hour and 20 minutes. We have a little more time this morning. So we don't have to, plus I simplified it. That's slightly simplified it. So we should have enough time to interrupt and ask questions. So feel free to stop and ask questions. Yeah.
Actually.
Finally, he's been waiting for 15 minutes.
Yeah. Now, the thing is that in this model that might come to question is what are the capability gaps between a device that only has like the hardware kind of TTP and the more soft TTP that supports multiple, like the ones directly matched to the user? It will be slower, it will be faster, or vice versa?
This is, so, that's an interesting question. So remember what we're doing here, no packets actually flow through these models. The packet, of course, flows through the silicon. The model is really a control model. So if you talk about the speed, we're not talking about the speed of the packet processing, we're talking about the control, the speed of the control. And I think that we're still working out how we do this mapping from a simple one to a complex one. But I think my guess is when we do it at the beginning, the performance will be okay. You know, the control performance. And then we'll figure out, okay, how can we do that more efficiently and so on. But ultimately, you know, it's like the difference between interpretation maybe and compilation. That like the initial one may be like roughly interpreted, but then maybe we'll figure out how to do it so that it's more of a direct, straight shot. There's other problems, I think. My sense of OpenFlow is that we have not been focused on performance, control path performance. And I think there's some improvements that are available really in the protocol itself. And we may move, I don't know, there's some discussion we're looking at now whether we should move from a protocol model to an API model, which might allow us to be a more efficient. But I think it makes more sense to focus on interoperability and compatibility and functionality, and then get the performance improvement. So I don't know, did I answer your question? Yeah.
So my question is, web applications Z is connected directly to the TTP device features, and while the application W is connected at the same time to the full abstract NBI and the A use cases roles. It looks like we exposed from the controller to the bound to several several sets of interfaces. It's full abstracted interface, it's use case interface, it's device features interface. Am I right?
Yeah, and I don't have the complete answer there, but there will be some things that are maybe new features or, so sort of...
Something like the experimental features?
Yeah, experimental features. I can see that some application, they know what's in this device and they want to use it directly. This is, like I say, more, and actually the point of these is to avoid device-specific features so that you can run on... Yeah, but if you're using some special thing, like you said, experimentally, this is the first chip that has it and you want to just like try it out in your lab or whatever, then I think you go here, but then over time maybe it migrates up there. These are still, these use cases are still sort of switch-oriented. It's an abstract switch, but it's still oriented toward a switch. As we move up the chain, then things become more service-oriented, may not be thinking exactly about a device, even a virtual device or an abstract device. You say, provide me a connection from this node, this end host to that server or something, and you're not thinking in terms of...
It looks like the network abstraction, the provider abstraction. So it's
Did you say in terms of ONOS?
Yeah.
Okay. And I'm not as familiar with ONOS. I'm a little more familiar with ODL. But yeah, so I would say this is the service abstraction layer up there in open daylight terms. And it sounds like, what did you call it?
It's called the network abstraction.
Yeah.
Network provider basics.
So yeah, there is, I think there is some hierarchy of abstraction there. And I think there's some of this even in so I kind of regard the controller as an operating system. I think other people say that as well. And if we look at an operating system, Linux or Windows or something, there's a bit of abstraction layers as well, right? Hardware abstraction layers. This picture, so this was why, okay, you may want to talk directly to this chip because it's some experimental new feature. In other cases, you say, well, I've got a soft device, it doesn't even have one of these. Like this might be NPU oriented. If you don't have one of these, it can speak whatever TTP you want. And so this model can also be supported. We haven't worked all that out. Our big focus is right here. If you had all NPUs, you wouldn't need this effort as much. But of course we don't. We don't have all NPUs. As long as we're talking about this, yeah, I'm happy to talk about that or this, the earlier picture. It came up in a recent discussion that basically what a TTP is, it's this model, but what it is it defines an interface. It defines what's allowed between, so I show it as a box, but really it's a line. And I show these as lines, but they're actually code. So I've kind of got it backwards. This is an interface from there to there, and this is an interface, kind of from here to the device. There is some logic in there, that code that we were like, is it interpretive or is it compiled? So this is a little bit misrepresented. I suppose each of the arrows is a little bit of mapping code, and this is just an interface. So it's slightly misrepresented. This is probably real code, but this is probably just an interface. So I have to work on that drawing. All right, does this kind of make some sense? It seems like, all right, what do you do with this, right? And that's why I think when we get down to the picture, you'll say, okay, this is what it is, and then you'll get, I think, a little bit better handle on how you use it. But it's still kind of early days. And OFDPA, how many of you have heard of OFDPA before this morning?
Here's about it, or just used it?
Heard about.
Heard about it.
Yeah. And I know people are using OFDPA. I talk about it like it's just a TTP or it is a TTP. And that's not exactly true. And somebody kind of reminded me that yesterday, one of my colleagues at the ONF. If you look at the OFDPA data sheet there, it is a model, but it's much more than a TTP. There's a bunch of code supporting it and so on, called the OpenFlow data plane abstraction. All right, so this is a picture of what the TTP, so this is our TTP. It's not a real TTP. It's kind of a exercise TTP that I invented sometime this past summer. And it's kind of, It resembles it, some real-world TTP, like the use cases we talked about, but it probably is full of bugs and stuff. I mean, it's just, it's simple on purpose, but because of the simplicity, it probably has some silly things, some silly ideas. But the idea is that it has 5 tables. I just want to show you some of the, like the syntax of it. It's JSON. You know, I used one of these tools. There's an online version, an online tool. If you just look up JSON editor online. It also, it says online, but it also has a Chrome plugin, and I like the Chrome plugin, so then I don't have to, I can, you know, when I'm on an airplane or something, I can still use this. I like that it's colorized, and so you can get a sense of it. But the truth is, I prefer not to look at TTPs that way. I kind of have to, given what I'm doing, but I think my next picture, well, we'll get to that. So, as mentioned, TTPs are built on OpenFlow. First, we think about what tables. So we keep looking at these pictures that have in OpenFlow itself, raw OpenFlow, every table can do everything. Every table is like super powerful. And you've probably heard about these TCAMs. You hear mentioned about, and you know what TCAM stands for? Yeah, TCAM is ternary content addressable memory. Ternary means it's not just binary, it's like 1, 0, don't care. So that's where the 3 comes from. And so it's like you have to match this bit or you don't care what this bit is. And OpenFlow kind of assumes every table is a TCAM, but real chips, you know, especially real ASICs, they probably have 1 TCAM, they might have 2, but they don't have 7, they don't have 20. They have a couple of 1 or 2 TCAMs, and everything else is a simpler table because TCAMs, they use more area and they use a lot more power. And so if you don't need a TCAM, you don't put a TCAM in there. We typically need to have a TCAM for ACLs, which are like very flexible matches. Then you need to have a TCAM. But for other things, if you're just doing a MAC lookup or if you're just doing an IP lookup, you know you're looking up a MAC or you know you're looking up an IP, then you don't use a TCAM. And so anyway, what we try to do when we're defining these TTPs or these pipeline models is we try to use specific tables when we can, and we use those very flexible tables only when we have to, like for an ACL. So that's what's going on here. We talk about what are the flow messages that make sense for this table. And if you have a narrow list of messages, not that much variability, that's good that makes it, you have a better chance that you can put that abstract pipeline on more chips. You know, the simpler the tables are. And then if you only have like 1 ACL or 1 kind of TCAM, 1 very flexible table, then probably they can figure out, okay, I know where to put that. That's going to go in my TCAM. OpenFlow messages, we usually call them flow mod messages, flow table modification, that even though they have other ones you can, other messages they can say. It seems like most people in the ONF call them flow mods. And so we say, well, what are the flow mods that are allowed for each table? And that's what we look at. Now, very often we don't say what is the exact flow mod message. You know, yes, there will be a MAC address, but I don't specify what the MAC address is. So there's really a range of flow mods. It could be you enter a MAC address, you can put in a port number, etc. So it's really a template. It's not a precise message. So each flow mod type is like a category of message. You know, you might have 50 entries that are that match this template, or you might have 5,000 entries that match that template. So there'll be lots of messages that match a template. In addition, we'll see, I'll show you in a little bit, there's sometimes where you want like default behavior. So you want to go from table 2 to table 3 whenever there's no match. And typically, if you look at OpenFlow, there's often a miss. So there'll be a miss entry. What happens if it doesn't match anything? What do you want it to do? You just want it to go to the next table, right? What if you left out your your miss entry, well then it's like something strange would happen. The ASIC can't do that. Basically, it would be a significantly different behavior if you didn't put the miss entry in versus if you did put the miss entry in. So rather than confuse things for the switch vendor, it's like, what if the guy never sends the miss entry? How do I can't support it. Then he would have to say, I can't support this TTP. So we said, well, rather than make that complicated assumption, because we believe, well, no, that message should always be there, that miss entry, don't worry about it, it's always going to be present. We call it a built-in flow mod, basically a built-in message. Assume that miss entry is always there. And in that case, that's a single message, a single flow entry. We have templates up here. You can talk about thousands of possible entries that match this template. In this case, like the miss entry, that's just a single entry. There may be other cases for a built-in flow mod, but essentially, maybe something that detects link layer packets or something, or topology packets, but some built-in thing, or that always drops. If suppose some switch might always drop packets that have a source address that's a multicast address. You're not supposed to do that. You're not supposed to have packets that are, and it could be that you can build in this message that says drop all packets received from a multicast address. That's a bogus packet. Anyway, so we'll look at that. So we basically describe what are allowed messages, and we'll take a look at that. And I think when you look at it a little bit, you'll say, oh, okay, now I understand what's going on there. Like I say, you probably won't be coding a lot of these, but you might very well modify one. All right, so this is just like in the earlier pictures we had circles or rectangles that move from one to the other. This was generated actually from the TTP. So I went through a series of tools, went through the OpenFlow tool, the Open Daylight tool. It generated this little snippet of text. And then you can take that snippet of text and run it through a GraphViz utility and get this graph here. That's not very exciting, but the purpose of this is to really just confirm, mentally I think we can draw this picture very easily, and so if it comes out of the tool, then it basically is a confirmation. Yeah, all right, that's working the way I expected. All right, so this was generated, as I said, we took the TTP, we ran it through Open Daylight with, well, not the full Open Daylight, but we ran it through the utility. We said, give us the dot. This is called dot language. Give us the dot language representation, and it generated that, and then I took that and ran it through the utility, and I got this. So, okay, I feel good about that. My TTP is, the basics of the TTP make sense to me. Now we're going to actually, the exercise that we have, which you're welcome to participate in, you're welcome to work together, you're welcome to ignore it if you want and check email, but if you want to, I'm going to walk through the different steps for how we modify the TTP and why you would modify this TTP. So essentially, we want to modify this TTP. Basically, we want a pipeline that does something a little bit different. Essentially, we want to be able to say, I want to route, typically, let me go back a step. The way this thing works, going back to here, this one, LLDP, all right, the first table we're looking to see, is it a link layer detection protocol? And if it is, I'm going to send it to the controller. And we can go look at the code. It actually has some match, and it looks and it says action, send a controller, or instruction, send a controller. Otherwise, then we're going to compare it, and if it matches our ACLs, the way I have it set up is a drop on match. We'll see that in a minute. So then there actually is sort of a way out of this pipeline in the first table. So if it matches and it's a link layer, send it to the controller, and it doesn't continue. There's another one here. If it matches the drop list, then it takes a side trip out this, it doesn't continue. And then our MAC is for the router MAC. Basically, the question is, the chip is asking, is this addressed to me as a router? If it is, then I need to route the packet. And I can do that, I determine that if it matches the MAC address of this router interface. Well, VLAN and MAC address. If it doesn't match the VLAN and MAC address, well, then I'm just going to switch it. I'm going to send it to my layer 2 logic. If it does match, then I'm going to send it to layer 3 and and route the packet. And there's different manipulations on the packet, right? Layer 2, if you're just switching, you don't modify the packet, you just send it on. If you're routing, then we need to change the MAC addresses, decrement the time to live. Maybe the time to live expires and we have to send it off for ICMP handling or whatever. But what we're going to propose here is that we add a capability. Well, I want to be able to route some traffic, even if it doesn't have the right MAC address. I still want to route it. And I've heard that some people do this. I still don't know exactly why, but in any case, what we're going to do is check in this one to see if it matches that funny flow that we want to route, but doesn't have the MAC address. And we'll bypass this check and we'll just go directly to the layer 3, to the routing logic. Maybe that doesn't work. Like I said, this isn't 100% real. But you understand the idea. Okay, I want to add a capability to this pipeline. Check and match, and instead of dropping it, I'm going to send it to layer 3. How do you do that? In OpenFlow terms, well, we'll see that. It'll be more clear. So we don't need a new table, right? So we don't have to create a new table. We're going to use an existing table. Use the same matching scheme that we use in our ACL. But the one we do in the ACL, right now, if it matches, we do nothing. And in OpenFlow, that means it drops. In this case, we're going to match on the same thing. Well, not exactly the same thing, because it shouldn't match exactly, but some 5-tuple, if you match that, it goes to routing. Other 5-tuple, if you match it, okay, that's a bad flow, and I'm just going to drop it. So the way we go to routing is we set up the go-to table instruction, and we'll take a look at that. And the way we look at that on the table graph, we already did that on the other picture. There'll be a new arrow when we're done. And we'll use our TTP editor for this. This is the thing that I got a little bit easier. So hopefully you can type that in. Basically, I have my GitHub account, and I figured out how I could host somebody else's. This guy, Jeremy Dorn, he did a great generic JSON editor. I say generic, you can control how the editor works using JSON schema. And the early version of this exercise, I made the people load the schema and a bunch of other things. It was very complicated and it was very hard to get. I mean, it wasn't super complicated, but it was kind of confusing. And I myself, when I was doing it, made several mistakes. Dave Lenro. I would plug the file, I'd drop it and paste it in the wrong place and so on. So fortunately we don't have that. I'm going to just leaving this up and I'm sort of blabbing for a minute in case you want to type that in your browser. Does everybody have a internet link? This isn't super high bandwidth, so hopefully you can get in there. If you want, we can do this afterwards. We'll be able to see how to do this. We can just do this on one crowd around a machine. Actually, I'm thinking we're about 1 hour in. Maybe I should take a break. I propose to take a 5 or 10 minute break. You can get on the internet during that time if you want. You can call up the editor, and or you can just do a bio break or whatever, get a coffee, and we'll see you back in about 5 minutes. Does that work?